Now we're going to compute some partial derivatives with actual functions. So remember that to find a partial derivative for a specified function, if we want to find the partial with respect to x, we treat y as a constant. So if you had something like f of x equaled yx squared, you would take the derivative kind of the way you would for f of x equals 3x squared. So remember, with the 3, it doesn't really factor into the derivative in terms of having to treat it specially. You can kind of factor out constants. So we would do the same thing for a y, but if we were trying to find the partial of y, or of f with respect to y, we would treat x as a constant and take the derivative. So we're going to come back to this. We're going to start over here. We want to find the partial with respect to x at this point, 1 natural log of 2. And the partial of y at the same point, partial with respect to y at the same point, for this function, x e to the x squared y. So let's think about this. If I want to find df dx, well, if this were like x e to the x squared 2, right, or 10x squared or whatever, we would still have x times an e function, so we would have to use the product rule. So to do that, we take the derivative of the first, hold the other constant, so that's 1 e to the x squared y, plus hold the first one constant, take the derivative of the second. So then we would take that partial there. Now recall that the partial, or the derivative with respect to x of e to the x squared, so the e to the anything, you have to use the chain rule, is e to the thing times the derivative of the thing. So that's going to be e to the x squared y plus x e to the x squared y times the derivative of the thing. So again, if this were 5x squared, the derivative would be 5 times the derivative of x squared. So this is x squared y, so it's y times the derivative of x squared. So you have 2xy. So then if I factor out an e to the x squared y, I get 1 plus 2x squared y. But I want to evaluate this at the given point. So 1 squared is just 1, so I'm not going to write that in. That's going to be natural log of 2. 1 plus 2 natural log of 2. Again, x squared, 1 squared is just 1. So we have e to the natural log of 2. Now recall that e and the natural log are inverse functions. So we can so e to the natural log of something is just that something, which gets us 2, 1 plus 2 natural log 2, or 2 plus 4 natural log 2. All right. So let's do the same thing with the partial with respect to y. We've only done the partial with respect to x here. Now with the partial with respect to y, what I notice is that if I hold x constant, well, this would be like saying if let's say x were 5, right? This would be like 5e to the 25y. Well, then that 5 doesn't really come into play in terms of the derivative. It's like a constant. So I don't really touch that. But I have e to something with a y, so I have to follow that chain rule. So it's x e to the x squared y times the derivative of x squared y. Now, again, remember, think of x as just some number. So the derivative of some number times y. So the derivative of 3y is just 3. So the derivative of x squared y is just x squared when it's with respect to y. So that's x e to the x squared y, x squared, or x cubed e to the x squared y. And then when we find the partial with respect to y, at the specified point, we get 1 cubed e to the 1 squared natural log 2, which is e to the natural log 2, which is 2. So notice that in this particular case, we get different values for the partial derivatives at the specified point. And that's kind of to be expected. You wouldn't expect the change in both the x and y direction to be the same all the time. Could be, but it's unlikely. So let's go over here. Now we've got something where we're taking a derivative with respect to z. So if I have df dz here, then I've got three things multiplied together. Now I have x and a y. Those are treated as constants when I take the partial with respect to z. Well, the derivative of a constant is actually 0. Now this would be like the derivative, think if it was the derivative of 3z squared, then it would be 3 times the derivative of z squared, which is 2z. But we don't have 3z squared, we have yz squared. So this is like y times that derivative, so 2yz. And again, the derivative of xz, if it were negative 4z, then the derivative will be negative 4. But we don't have negative 4, we have xz. So we take the derivative of only the z portion. And I want you to notice something here as well. Just because I take a partial with respect to a particular variable, it doesn't erase the other variables. Notice that this function here still contains x, y, and z. And why is that important? It's important because when we start thinking about the idea of second derivatives, we're going to be using these. So I might take my first derivative with respect to one direction. I might take my second derivative with respect to a different direction. So it matters that we have these variables here.